Hello and welcome back to the chemistry of indoles. So last time we were discussing the reactions where we talked about the Plancher rearrangement. Now let us consider the acidity of indole. The NH bond, just like that of pyrrole, is acidic, so you can abstract it with a suitable base. The pK value is round about 17, so it's close to an alcohol's acidity. So strong bases like sodium hydride in DMF or sodium amide in liquid ammonia or potassium tertiary butoxide in tertiary butanol or any organometallic reagents such as N-butyl lithium in 3HF or methyl magnesium iodide in ether can be used to deprotonate these molecules, and with the exception of the Grignard reagent, the other sodio derivative or potassio or lithium derivative, they are pretty much ionic in nature, whereas the organometallic reagent, Grignard reagent, deprotonates this hydrogen and generates a roughly a covalent compound where there is a significant covalent interaction between the nitrogen and magnesium. All of these N-metallated indoles, be that sodium or potassium or magnesium or lithium, they can react with electrophiles and they are ambident in nature. They have the possibility of reacting at nitrogen or at the C3. But as you know that from your discussions in pyrrole, if the ionic character of nitrogen is high, then the reaction will be at the nitrogen. But if the nitrogen is sort of covalently bonded with the metal, then it is the C3 position where this reaction will take place. So it does not come as a surprise that when you are using sodium or potassium salts of indole, then you are getting and finally you are treating this thing with the electrophile. The electrophile is going into onto the nitrogen. So here you have deprotonation with sodium hydride. So this here will be generated the sodium derivative. Then add methyl bromide, so you have N-methyl. Then you have petrosylation reaction. Then you deprotonation with potassium hydroxide in DMSO. See, the DMSO in DMSO medium potassium hydroxide is a much stronger base because there is no hydrogen bonding from the protic solvent. DMSO is a polar aprotic solvent, so KOH is soluble there, but hydroxide is orphan, kind of, because there is no hydrogen bonding to stabilize it. So its reactivity as a nucleophile as well as a base is very high, and therefore it deprotonates this hydrogen very happily. And the benzylation reaction you can do on nitrogen because this is a potassium derivative. Same thing can happen with potassium hydroxide using presence of a crown ether like 18 crown 6, which is a specific crown for potassium capture, and therefore hydroxide is free. In benzene, hydroxide is extremely reactive, therefore this deprotonation can take place and you have a ethylation reaction. With sodium hydroxide in dimethoxyethane, the same philosophy. Dimethoxyethane is again a non-protic solvent and you have a benzylation reaction on nitrogen. This one here is a little bit interesting. This is, you are deprotonating it with a dimethyl aminopyridine, DMAP. N-dimethyl aminopyridine. So you have a pyridine nucleus and it's on its 4 position you have an NME2 group. That's the base, deprotonation with that base, and you are treating this thing with BOC2O. What is BOC2O? What is BOC? BOC is tertiary butyl oxycarbonyl. Okay, tertiary butyl oxycarbonyl. So that's basically a kind of a anhydride kind of thing. You have anhydride kind of thing, and you are introducing a BOC group, a tertiary butyl oxycarbonyl group here. This N-BOC is, as you know, you have probably encountered that when you talked about in your last semester when you talked about the protecting group chemistry. A nitrogen's protecting group, they are like 3 different protecting groups. One is the FMOC, the other was the BOC, and other was the CBZ. So these are the urethane linkages that you are establishing, and when you treat this thing with a little bit of acid, this undergoes the AAL1 cleavage, so this goes away as a carbocation, this becomes a carboxylic acid, and overall this molecule becomes a carbonic acid derivative and ejects the nitrogen part very easily with decarboxylation. On the other hand, if you have magnetio indole, those are covalent in nature, and this time the functionalization of those metallated indoles will be taking place preferentially at the C3 with a partial negative charge here you can draw the resonance structures like that, and therefore it is the C3 position where the alkylations or the acylation reactions are happening. You are treating it with epoxide, so you get a 2 carbon electrophile introduced here, CH2 CH2OH. You are doing with heteroaromatic aldehyde, so this is a secondary alcohol that you get. Alylation reaction in presence of the benzene at room temperature will give you the 3-allyl indole. With alpha beta unsaturated acid chloride in presence of a zinc chloride Lewis acid, you will get a C3 acylated indole derivative. So these reactions are basically reminiscent of those that you have already seen for pyrrole. So these are not very new. Now C-metallation. Well, first of all, C-metallation cannot be done unless you protect the N hydrogen. This is a much more acidic proton compared to this one, or any other protons. So if you want to deprotonate any of the CH bonds of indole, the very first thing that you need to do is to block this NH. And this C-metallation will become important because till now we have not found a method to functionalize the C2 position of indole. In the last lecture we talked about this, that how to functionalize the C2 position. The C3 position can be functionalized by aromatic electrophilic substitution. You know that the propensity for the C3 substitution in aromatic electrophilic substitution for indole is so great that even if the C3 position is occupied, the electrophile gets introduced into the C3 position and then it migrates to the C2 position. So if I want to selectively functionalize the C2 by not disturbing the C3, how to do that? To do that, you need preferential abstraction of the hydrogen from C2. That makes sense because the inductive effect of this nitrogen will be greater at C2 compared to at C3. Therefore, you can possibly deprotonate here and not deprotonate here, but that will require absence of this much more acidic NH bond. So you need to abstract this and protect this nitrogen in the form of, say, N-acyl or N-sulfonyl indoles, and those products or those protected derivatives can be safely lithiated at C2 by treatment of organolithium reagent. And those groups that you are introducing on nitrogen to protect not only the inductive effect of the nitrogen but also the coordinating capacity of those oxygens with the lithium of the organolithium reagent, just as you have seen for directed orthometallation when we discussed the organometallic chemistry. That will guide the organolithium reagent and preferentially abstract and make it preferentially abstract this proton here. As you can see, we have taken indole, we have done a deprotonation reaction with sodium hydroxide in presence of a phase transfer catalyst such as tetrabutyl ammonium hydroxide in dichloromethane medium, and then we have treated with the benzene sulfonyl chloride. So you have got a sulfonylation reaction here and you have a SO2 pH group introduced on nitrogen. So there is no more NH bond. So you can now go for deprotonation of this hydrogen. So you can add an N-butyl lithium at minus 78 degrees centigrade. You can see that the lithium is coordinated with the oxygen and that coordination stabilizes the anion, and this is the steering effect or directing effect of the N-sulfonyl group, which makes this organolithium preferentially abstract this C2 hydrogen and not the C3 hydrogen. Once you have done that, this is a very powerful nucleophile. You have a negative charge here, and therefore you can have introduction of an electrophile here, just as we have done with acetophenone. So you get a tertiary alcohol, and then you need to knock this thing out. You can do that by aqueous NaOH. Sulfonamide hydrolysis will take place, and it will liberate your C2 functionalized indole. The other thing is that you can use the T-Bock or the Bock. People call it T-Bock or also called Bock. So you have Bock here, and N-butyl lithium treatment will give you the lithiated derivative at C2. This will be coordinating with lithium, and therefore this is a stabilized complex. That is why, and also the minus I effect of nitrogen makes the C2 hydrogen being preferentially abstracted. Then you are treating this thing with N2O4. TBOC is going away in this step as you are heating this reaction mixture from -120 to 0 degrees centigrade, and you get an introduction of a nitro here, and then you treat it with, if you treat this thing with a dimethyl oxide, so you get a CO2Me here, and then you want to knock this thing out, just as I have told you, you treat it with trifluoroacetic acid at room temperature. So this tertiary butyl group will go by Al1 cleavage. This will become carboxylic acid. This is nothing but a carbamic acid derivative. Automatically decarboxylation will take place and you will liberate your indole derivative, C2 functionalized indole derivative in the reaction medium. One of the most beautiful protocol of C2 functionalization was developed by Alan Cartridge, who was a famous heterocyclic chemist. He has lots and lots of publications, and he did enormous work on the field of heterocyclic chemistry, and he was in the Florida State University, FSU. So he took indole and then he treated this thing with N-butyl lithium. So obviously your NH proton is deprotonated, and then he added carbon dioxide. So carbon dioxide is the electrophile, so you get a NCOOLI. So a very simple protecting group, no TBOC, no SO2pH, nothing, just carbon dioxide. Once this nitrogen is protected in the form of N-carboxylate salt, you treat it with tertiary butyl lithium so that your C2 hydrogen is abstracted, facilitated by the coordination of the lithium with the carbonyl oxygen of the N-carboxylate group. And then you add an electrophile, where this electrophile is included here, and then H3O plus treatment will protonate this, and this will become a carbamic acid derivative. Decarboxylation will immediately follow, and it will give you the C2 functionalized indole. I have given you two examples because of its usual mechanistic, because the mechanism is usually very interesting. That is why I have given you. So they have introduced iodine, but not in the form of iodine, but in the form of ICH2CH2I. They have introduced bromine, not in the form of Br2, but in the form of BrCCl2CCl2Br. So what is happening here? These are very interesting things that you may look into. But of course, you can use other electrophiles such as this one, that one, or maybe electrophiles that are listed here. All of these will be introduced into the C2 position, and after that you acidify. So you get your, instead of the lithium carboxylate, you get the carboxylic acid, and instantly it decomposes, decarboxylates, liberates the C2 functionalized indole in the reaction medium. The very last reaction that we are going to discuss in our course, because indole has so many reactions, we have discussed only a small fraction of it that is suitable and pertaining to our course. But that last reaction is the decarboxylation of indole carboxylic acid. These two molecules here, this indole 3-carboxylic acid, and this one is the derivative which can be thought of as a derivative of acetic acid, where one of the acetic acid methyl hydrogen has been replaced by indole, and the connection point with indole with the alpha carbon of acetic acid is the C2 position. So people call it 2-indolyl acetic acid, 2-indolyl or indole 2-yl acetic acid. You can also add a 2 in front of that thing to understand that this is 1 and this is 2. But indole 2-yl acetic acid, that name is also sufficient. Indole 2-yl means the indole group has its point of attachment at C2, and then you have the acetic acid. So where can you add the indole group at acetic acid? Most reasonably at the CH3 position. And this one is simple, carboxylic acid at C3 position. So when you boil these acids in water, they decarboxylate readily, and their reaction takes place via the C3 protonation. As you know that C3 protonation will be much more favorable than either N protonation or C2 protonation. And once the CH bond has come here, once you have protonated, it is a decarboxylation reaction triggered by the protonation. So it is a proto-decarboxylation, that's a ipso substitution. This is basically an aromatic electrophilic substitution. No, where the incoming electrophile is H plus and the departing thing is H plus is leaving and the carbon dioxide is also leaving. So you can see that it is a ipso substitution. In this case, it's a little bit different, but the reaction starts with the protonation at C3, and then you decarboxylate from the C2 position where you are left with a carbon-carbon double bond. But that is a tautomeric change which is inevitable to happen, and it will give you the 2-methyl indole. Indole 1 carboxylic acid. That's a Katherich's work, no? You have CO2Li here. After you protonate, you get CO2H. So that's indole 1 carboxylic acid. That's a carbonic acid derivative. It decarboxylates very easily, and carbonic acid is even more unstable. Indole 1 carboxylic acid can be isolated and characterized, and can be used for the acylation reactions, as you have seen with the lithium salt. But still, its decarboxylation is relatively easy. Indole 2 carboxylic acid, on the other hand, that can only be decarboxylated with much more difficulty. For decarboxylation, you will need some sort of copper, salts, and also quinoline must be present, and that is how you prepare the indole nucleus itself by Fischer-Indole synthesis. We have already talked about this, that you cannot take acetaldehyde and treat it with phenyl hydrogen to get the corresponding phenyl hydrogen, and then cyclize it via Fischer-Indole cyclization in presence of a Lewis acid or a Bronsted acid to get indole, because acetaldehyde is so reactive that side reactions take place. Instead of indole cyclization, side reactions will happen. Pyruvic acid or ester of pyruvic acid can be used for that purpose. If you use pyruvic acid, then you have phenyl hydrogen of pyruvic acid when treated with phenyl hydrogen in presence of sodium acetate under properly buffered solution. And then treatment with zinc chloride will cyclize the ring to give you the indole 2 carboxylic acid, which was then subjected to decarboxylation reaction, but it took some effort, not like this, boiling with water, not like that. You have to do it with copper chromite and quinoline, and then heating will give you the corresponding indole. So indole can be prepared by Fischer-Indole synthesis, but remember, do not start with acetaldehyde. You do not take a H here, you take a CO2H. We have seen so many occasions where a CO2H can substitute, can act as a surrogate for the hydrogen. You have seen many different occasions. Say, for example, you saw that in the bromination of cinnamic acid and subsequent treatment with sodium carbonate, where decarboxylative dehydrobromination took place instead of a simple dehydrobromination. So here again, the CO2H group is acting as a surrogate. The indole 2 carboxylic acid is actually stronger than corresponding 3 radioisomers. So this one is actually a stronger acid compared to that one. So people might expect that, when you dissolve this thing in water, the proton concentration of the H plus concentration of the solution will be greater than that, because this is a weaker acid, that is a stronger acid. So protons are much more available, so proto-decarboxylation should happen with indole 2 carboxylic acid just as it was happening with indole 3 carboxylic acid. But the problem is, for this decarboxylation to happen, the protonation will have to be at C2. Otherwise, the decarboxylation will not take place. Proto-decarboxylation will not take place. Ipso substitution, for that to happen, you need to protonate here. And for decarboxylation of this one, you need to protonate here. That is C3, and that is C2. We know that C3 protonation is much more favorable at indole nucleus. And that is presumably why the proto-decarboxylation is so facile for the indole 3 carboxylic acid and not on the indole 2 carboxylic acid. So this much for the chemistry of indoles. I thank you for your patience, and I will be seeing you as usual in the next one.